Okay, welcome back here. We are continuing on. Well, we just had our 20-minute break, so this is lecture 2 for today, and this is lecture number 11, and we've been working on 13. Let's wrap up 13. There's still some really neat things in the structure of matter, and then we're going to shift gears. But I want to emphasize, as we get started into the next chapter, which is 15, that part will not be on the exam. So let me say it again. You have an exam coming up. It's this Monday, 11 o'clock. This Monday is the 15th, and so June 15th at 11 o'clock, sit down there in front of that computer and take that test. You'll have an hour and a half plus 15 minutes to take it, scan it, and send it up. And it'll be a lot of these, type of things, including those tougher calculations that I was just showing you in the last little video. As I continue on here, your author has a few more things, and he begins to ask this as we wrap up our structure of material. And I'll just draw a picture here. For the last couple of lectures, we've been saying, okay, if you have something that's hot, and you put it next to something that is cold. At the last lecture, I said let's take that to be an aluminum and a lead piece, and I let these little dots represent the atoms of aluminum, so let me do that again. And then I had some more dots representing the atoms of the lead. Let me do that again. And we said, well, let's say our piece of aluminum is hotter. And so we had a 50-degree piece of aluminum, if you remember, and it was a 20-degree piece of lead. And we went through some calculations to find out that if we had this 90 grams of aluminum and 300 grams of lead, that the final temperature is roughly around 40. If I remember right, it was like 40.3 degrees Celsius. And so the energy would move from the hot one to the cold one. And all we calculated in the last bit was what the final temperature would be based upon the final amount of energy that transferred. What we didn't do is ask the question, how does the energy get transferred and at what rate? In other words, we know the final temperature is going to be 40.3 degrees Celsius, but will it be that in 1 minute, 1 second, 1 hour, 1 day, 1 week, 1 month, 1 year? I mean, how long will it take? And that's the last part of this chapter. And it turns out that there are 3 mechanisms of how the energy transfers from one to another. The first one is called conduction. The second one is called convection. And the last one is a word called radiation. And let me just point out, sometimes when that word is heard, people associate it with radiation, bad, cancer. That is not what a scientist means by radiation. And so the radiation we're talking about is anything that radiates. Bad stuff radiates, but also good stuff radiates. So we're going to look at some good radiation, not bad radiation. So we call it radiation. Thermal radiation, to be a little more specific. But the first one, and the easiest one to kind of get you to understand, is called conduction. And I like to put these words for conduction. I would say conduction is the transporting of thermal energy. So I'll just say thermal energy transported via, and the way it happens is with collisions. I'll try to create a mental picture for you. But if I come back to this little drawing over here, the reason I would say that aluminum is hotter is because the atoms of aluminum, on average, the higher temperature, remember temperature has to do with average, they're moving around a little bit faster. But right next to this aluminum one are these lead ones. Now these lead ones are moving slower. That's why we say they have a lower temperature. And so you could imagine if you took something that was moving fast and you put it next to something that's moving slow, and so this fast one bumps into the slow one. As they bump, the slow one then gains some speed. Towards the slow one picks up some speed. And in the process of the collision, the hot ones, the aluminum ones, slow down. And that's what is called conduction. It's nothing real fancy. You might just say, if you took the first layer of aluminum atoms that are moving fast, and they bump up against the first layer of lead atoms, which are moving slow, what ends up happening is the aluminum ones slow down and the lead ones speed up. That is what I mean by conduction. This is how the energy actually moves. They just make the slow ones, the lead ones, go faster, and then the fast ones, the aluminum, slow down. They just bump right into each other. Those are called collisions. And of course the process would continue layer by layer, because the layer that's right behind the first layer of aluminum would still be going fast, but then they would bump the first layer of aluminum that has now slowed down, and that would pick up their speed again. And likewise for the lead. The lead, the second layer back, which is going slow, then bumps into these fast-moving lead ones, the first layer, and makes them go fast, which slows down these lead ones. So after a bumping of the second layer, you get now fast aluminum ones next to slow lead ones, which the process kind of starts all over again. The fast-moving aluminum ones then bump into the lead. The aluminum ones slow down. Now the lead ones speed up. And then, of course, this all repeats again for layer number 3. Because layer number 3 back here with these aluminum ones are still going fast. And now that the first 2 layers have slowed down after what I'll call the second bumping, they get restarted, if you will. They get re-sped up because of this third layer. And, of course, the same thing happens but in reverse for the lead. The third layer, still going slow, begins to speed up because the second layer now has sped up because it bumped that first layer in what I'll call the second round. And so now we start round number 3. That is, once this first layer has sped up again because of the bumping from the third layer went over to the first layer. And likewise, the first layer of lead has now slowed down because it then sped up the third layer of lead. We now have aluminum and lead next to each other, and this is what I'll call round 3. Well, I hope you're getting the idea of this, and there'll be a round 4 and a round 5 and a round 6 and a round 7. And so layer by layer, the energy begins to move via this bumping from the hot object to a cold object. And that's the mental picture here here by conduction. It just literally, they bump one into another. And what I want to emphasize, because you'll see me say that this is the important difference between conduction and convection, notice then that this cold object, the lead, is gaining energy. But never did any of the aluminum atoms actually go over to the lead. Right? There was not a transport of material. The aluminum atoms never went over to the lead, but the energy did. So the aluminum ones lost their energy. They did not lose atoms. They lost energy. And that process is referred to as conduction. And if I took then a metal rod, and so I'll just draw sort of a metal rod here, and I put the far end of the metal rod in a flame, this flame, and being hot, means that the atoms on the outside of the metal bar are going very, very fast. That's why we call them hot. They then bump into the atoms that are at the end of this metal bar. And maybe I'll just say this metal bar is made out of copper. So I've got this copper metal bar. That one end of it, they're going very fast. And of course, they would bump the next and 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 bump the next. And then over here, eventually, not right away, but eventually, the end of that metal bar will get hot. That process is conduction. That's how the energy moved down this metal bar. That's how the energy moved from this aluminum piece to this lead piece. The bumping of those atoms. And then you could probably imagine then that each material, copper versus aluminum versus lead versus steel versus wood, would all bump at a different rate. And so I want to turn on your book here for a second and look again at this chapter 13, and table 3 right here shows different materials, and it says, look, these materials then will allow energy to go through them. They just take a while. And they're not the same. And so there's some numbers. Now for our class, being Physics 102, I will say that I'm glad he gives you this chart. He actually gives you some numbers, but he stops short of doing any calculations. And so this is more of a conceptual discussion than it is a numerical calculation. And he points out that there are some numbers here. He rates them in watts per meter for each degree. Okay. But let's look at some of the solid ones. As I said, if I was looking at copper, copper gives a number of 401. Now, if you look at all the other numbers up here, you'll see 401 is on the high side. There is silver, which is a little higher than that. But silver or copper are way up there in the numbers. Aluminum is only about half of that at 213. And then look at stainless steel. Stainless steel is actually really small. It's down at a 14. But what these numbers are saying is the rate at which the energy gets transmitted. Okay, and so here I would say if you want the energy to conduct, if you want the heat to flow, make it out of something like copper or silver or even aluminum. Silver, of course, gets very expensive. So I'll show you some experiments and you'll see I never use silver because I just can't afford anything with silver to show you. But copper's not too bad. And then aluminum's pretty good also. You'll see later on when we get to convections, I will show you these heat sinks. And these heat sinks and these here are really nice because they're made out of aluminum. And aluminum conducts really well. Now, as you can see, not really as good as silver or copper, but still, as you will see, it's still up there really well. If we look at some of the ones that don't transfer heat very well, maybe I'll pick on wood here. Wood is really small, and so it's hard to get the energy to go from one side of a piece of wood down to the other side of the piece of wood. So keep that one in mind, because your author then shows you a really neat picture of a home in wintertime with some snow. And so I guess for those of us here in Santa Barbara, we have to kind of imagine what snow is again. But look carefully at this house, particularly at the snow on the roof and the conduction of it. And what I mean by that, and you see it off in this room the best, you'll see that the eaves, because under the eaves is just outside air. So down here, I guess is this a eave and a rake? Or no, rake and an eave? This one, yeah. Anyways, I'll just call it eave. Underneath is still cold, but under the roof, I would assume here is the attic, which is connected to part of the house, and so that's warm. And so what happens is the heat is conducting through the wood and melting the snow. Now, hopefully not very fast. Otherwise, the people in this house will have to have a big heater and pay a lot of money to heat the house. So the roof is made out of wood, probably even has some insulation in it, but it nonetheless is still conducting through and melting the snow. And for some reason, oh, I'm sorry, this is the garage. That's the reason. I didn't recognize that as a single car garage. Okay, but the garage then has probably less of insulation here and has melted the snow quicker than the house part of it. And even though the house is probably warmer, in addition to the wood, they probably have insulation over the top, and they don't do that in the garage, although the garage is probably also a little colder than the house. You can see it melt. Well, I don't know if that was a very good picture there, but I thought I would grab it before I jump to my experiments. But what I really like in my experiments is this, what we call the conductometer. The conductometer is a way to measure conductivity. How quickly are these? If I hold this up, and maybe I'll hold it this way to the camera, you'll see that I have a hub, and at this hub there are 5 pieces of metal radiating out from the hub, okay? Because what I'm going to do is I'm going to put this in the flame here. And I'm going to put the hub in the flame. And what that means then is one end of every rod is going to get hot. And then it will conduct the heat down the rod. And the ends of the rods have these red things on them. Those are just plastic or wax. They're wax from a candle. And when they get hot, of course, the wax melts. So it doesn't take much of a temperature to melt wax. And so we'll see which ones fall off first because they get hot. And so if I begin this experiment, there we go. I always forget that it won't start when it's in the flame. And I come over here, and I sneak it in here real well, there we go, and try to hold it equally in the middle. Not so easy to do, but I am hopefully warming one end of every rod equally. And I will tell you, these 5 are different metals. This one over here is the copper. And I'll point it out first because I don't think it'll take long before this wax piece falls off. Remember, I just showed you copper conducts really, really fast. And I don't know if you can see, but it's already dripping. And now it goes and falls off. Now, this one's brass. There it goes. And so the brass apparently conducts like the copper, but a little bit slower. So I took a little bit longer, but it was pretty close. And there's the wax on the end. Here is nickel. This one here is iron. And this one here is stainless steel. Now, if you remember the numbers I was just showing you, remember the stainless steel was only 14. Of all these metals, the one that conducts the most is copper, and the one the least, stainless steel. And of course, copper was way up there, so we saw that one. Oh, well, there goes the, and there goes the nickel. And iron and nickel are about the same number, so you can see that. And then the stainless will take a lot longer, so I'll just stop because we'll be here till Christmas waiting for that one to fall off. But that's a really good experiment of showing you that they all conduct, but they do it at a different rate. That's what conduction is. And for our class, we won't do any calculations. We'll save that for Physics 123. But at least you can see the numbers in the chart, and we can talk about them conceptually. In fact, it's why I kind of like this one here. This is kind of one of my favorite ones to do. Is if I were to take 2 rods, but as hopefully you can see on the video, one rod is made out of a metal. This is just iron, and this one is made out of wood. And I put a blue piece of paper on each of them, just kind of taped it on here. Because most people say, well, if you put paper into a flame, it will catch on fire. Maybe. You see, temperature of the paper is real important because it won't catch on fire until it gets up to the burning point of paper, which if any of you remember your high school reading in your Ray Bradbury science book, you remember that Fahrenheit 451 book? Remember it was based upon the temperature that paper burns at. So the temperature that paper burns at is Fahrenheit 451. That's the title of the book, right? That's the whole story. Well, that's the title of the story, I guess, is about burning books. But that aside, the title, Fahrenheit 451, is telling me the temperature. So if this piece of paper gets to a temperature of 451, it'll catch on fire. The wood is important. Do you remember that chart I was just showing you? Remember the conductivity of wood is really low. This flame is about 1,000 degrees Celsius. So Fahrenheit. Let me take this piece of paper. Let me hold it maybe about this high off the flame. And nobody's really surprised when the paper catches on fire because the molecules on the outside are 1,000 degrees Fahrenheit. They hit the paper starts to warm up. Now, the other side of the paper hits the wood, tries to give its energy to the wood, but remember the wood doesn't conduct it away, and so the paper ends up getting warmer and warmer, and eventually gets to 451, and eventually catches on fire, and even gets hotter than that. And so the paper catches on fire. Like I said, nobody's surprised with that. But I think the fun one to see is the same experiment done where I take a piece of paper and I wrap it around a piece of metal. Because here, the paper doesn't catch on fire. The 1,000 degree Fahrenheit on the outside hits the paper. The paper then hits the metal, and the metal conducts it away very quickly, and now the paper cools again. And so, quite surprisingly, even though the paper is in the flame, it doesn't catch on fire. It conducts it away. Now, of course, eventually this metal rod will get hot. Eventually the metal rod will get up to 451. Eventually the piece of paper then will catch on fire. I can already feel it getting warm in my hand, but I'm not going to hold it until it gets to 451 degrees Fahrenheit. You can even see kind of a little singe on it, but very little. And that's kind of the neat thing about conduction. In fact, it kind of reminds me, if I can talk about a cold day again, as I was saying before the break, you might have to go all the way back before school ended here, back in February. But in my house, when I get up in the morning, I have like a little throw rug under the bed and in the bedroom, and so I step on carpet. But as I take a couple of steps, I then get to hardwood floor. And then, of course, if I go down the hallway on the hardwood floor, I then get to tile that's in the kitchen. And so if I get up and I walk from the carpet to the hardwood floor, and I'll just do hardwood floor, it's even more true for the tile, but it feels colder on the hardwood floor. The tile even feels really cold when I get into the kitchen. Is it colder? I mean, the whole house has been sitting in the same place. Is it really colder? Especially when I'm in the bedroom. If I put one foot on carpet and one foot on the hardwood floor, I'm like, this hardwood floor feels colder. I wonder why it's colder. But if I take a thermometer and I put it on the hardwood floor and I put it on the carpet, I will find out they are actually the same temperature. So why does it feel colder? And the answer is just what you saw with this paper, with the conduction. You see, when my foot, which is warm, steps on the cold carpet, it warms the carpet right underneath it, but the carpet is a poor conductor, so it doesn't pull that heat away. In other words, the carpet right under my foot, because it was warmed by my foot, stays warm. But the tile is a different story. When I step on the tile, my foot warms the tile under my foot, then it conducts it away, So the tile that's under my foot is still cold. So my foot warms that, and then that conducts away. And then it's still cold under my foot. And so my foot does it again and again. So it stays cold. So it's not that it's a lower temperature, but it does have to do with the conductivity of it. And it gives it that different effect, that feel of it. Remember I said silver was a really, really, really good conductor? Copper just behind that. That's why in my little conductometer I had a rod made out of copper. I wish I had one of silver, but like I said, I can't afford that much silver to add on to here. But a piece of silver that if you have fancy silverware, and in my case, my mom's got this fancy set of real silverware. It's not stainless steel silverware. It is literally silver. That's why it's called silverware. And she brings it out every Christmas and Thanksgiving. And obnoxious thing about silver is it tarnishes. So she gets out, she polishes it all up for the Thanksgiving and Christmas. All right, so when she gets it up and makes dinner, and then I usually do the cleaning and the picking up, I will take the silver. And then when I put it in the dishwasher, it runs through its cycle and it gets really, really hot. And then I go to unload the dishes. And I reach in and I grab a hot spoon. And if I grab the real silver spoon, it burns me. I have to let it go. If I grab the stainless steel spoon that maybe we had just lying around for the coffee or the tea, it's hot and I just go, ow, 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 and I put it in the drawer. But it doesn't burn me. Is it somehow hotter because it's silver? No, they were both in the dishwasher. They're both at the same temperature. But the silver conducts really well. That's what this is showing. And so if I grab this, then in the case of wood, this would be like the stainless steel, which remember, the stainless steel is the one that doesn't conduct very well. This is this one right here. And so if I grab a stainless steel spoon, what happens is my fingers cool it down, but the heat in the rest of the spoon does not conduct up, and I can therefore hold it and put it away. But the real silver, it feels totally different. You grab that real silver spoon and it's hot. And then it conducts up and it's still hot. And then it conducts up and it's still hot. And all that heat's going to your hand. And by the time you lift it up, you just got to let it go. It's just too much heat. And it feels hotter, but rest assured it is not. Now, I haven't had this experience, but for those of you who will wear jewelry, and particularly earrings. I know my wife had this experience. We went skiing, and she had real silver studs in her ears. And it conducted the heat so fast. I mean, just 10 minutes out on the slope, she'd go, "My ears are so cold." It's like, well, you got your silver earrings in. You're supposed to wear stainless steel when you go skiing, so you don't have this problem. Like, oh, well, I didn't know that. So, lesson learned. And so we learned that, hey, wear this cheap stainless steel jewelry, like your rings and your necklace and your earrings, because they don't conduct while you're skiing. Stay away from the real silver stuff. It conducts really well. In fact, it also reminds me, I better move on, but funny story I saw. I guess it was funny because it didn't happen to me. I guess the word is ironic because it's really not funny, but I still laugh about it. Is I was watching, and I was a kid too. We were on vacation, family. We had gone to Palm Springs in July, so it's blistering hot. I'm sure we went there because as a young kid we had no money, and it was like, oh, okay, dirt cheap in Palm Springs in July because nobody wants to be there. So we went to Palm Springs, and it was for us it was a big vacation because we actually stayed in a hotel with a pool. Like, oh wow, big deal. So we're staying there, and me and my brother go, hey, across the street is an ice cream place. Let's see if we can get some money from mom and dad. Let's go get some ice cream. So we got some money, and we go across the street. Of course, we weren't used to Santa Barbara. We just go barefoot. Well, we walk outside of the pool, and we start walking on this black asphalt, getting across the parking lot to the ice cream store, and it's hot. It is really hot. And we're putting our feet down going, ow, ow. And we probably should have gone back and got shoes. But, you know, hey, we're only 10 years old. You know, why go get shoes? And so we realized that there's a bunch of cars, and they're parked in their shade. So we would run from car to car to car to car. And it was really hot. And we get pretty much all the way through. And on the other side of the parking lot, there's another kid doing the same thing. And he's running from car to car, and he's barefooted. But this kid, going across the driveway, there is a metal manhole cover. And when he stepped on that, the conductivity was so much more than the black asphalt. I mean, they both were hot, and they were both the same temperature. But just the stepping on it was so much hotter that he just like grabbed his foot and kind of hobbled the rest of the way. And when we went over to see how he was doing, it actually blistered his foot. His foot had blistered because of that conductivity. So it could make a big difference, and that's what I'm trying to get at here. Well, let me show you a couple other fun ones here. I still got my ice over here, and let me grab this cup because, again, just to see the difference in conductivity is kind of fun. So I will put a chunk of ice on a piece of wood, and of course the heat will conduct up from the wood into the ice and begin to melt the ice. And so over the next 20 minutes or so, let's watch it melt. And as it melts, of course, the heat's coming from the wood. But you might also see that I have a shiny metal plate. This is a stainless steel plate. And so if I put a chunk of ice on the stainless steel, you'll be able then to get a comparison between the conduction of the stainless steel and the conduction of the wood. Now, as I said, stainless steel does not conduct well. But it does do better than the wood. So we will hopefully see the ice melt a little bit faster on the stainless steel than the wood. In fact, I think you might even be able to see that already. I could see a little puddle of water coming underneath this ice. But the really fun part of this is to put it on a block of aluminum. And so I got these 2 blocks of anodized aluminum here. And so if I put this on the aluminum, now remember, the aluminum, the conductivity is really, really, really fast. This is so fast that even in this short amount of time that I've put there, I think you can see more has melted now on this block of aluminum than the wood or the stainless steel. And so as I stand back and look at it, I can see a puddle of water already on the aluminum. I'm beginning to see a little bit of water on the stainless steel, and I see almost no water yet on the wood. And so again, it's showing me the conductivity. And I always just find it amazingly just to watch how quickly that piece of ice will melt when it's on a piece of aluminum or a piece of copper. It's why I couldn't resist buying one of these infomercial things. I saw this infomercial, and for $20 it was this magical, the Defrost-O-Matic. And all they had to do for 20 bucks is buy this. And you put your frozen chicken on here, your frozen burrito on here, and within a couple minutes, it's defrosted. And I suppose the good news is it does work. The bad news is it's just a chunk of aluminum. I could have bought this for 50 cents. Instead, I paid $20 for a piece of aluminum. But that's the whole idea of this conductivity here. Well, I'll show you one more conductivity, and it leads to this second idea of convection. And I'll start with a question that might seem a little funny, and I hope it does. Could you boil water in a paper cup? Well, again, I think most people's first reaction is, no way. You put paper in a flame, it catches on fire. Oh yeah, really? Does it? Did this catch on fire? it won't catch on fire until it gets to a temperature of 451. And do you remember on the Fahrenheit scale what temperature water boils at? Do you remember it was 212? See, I will actually try this. Let me draw a picture here first. But if I take a cup filled with water and I put a flame underneath it, even if that flame has molecules that are so hot that they are 1,000 degrees Fahrenheit, and that's what I have right here. I'll start getting ready to set it up here. Here's my burner. Here's my 1,000 degrees temperature. My paper cup, what I do with it, is over here. My water is right here. And so if I put this paper cup on the stand and I move the flame underneath it, what'll happen first? Will the paper catch on fire, or will the water boil? And I want you to see that the water will boil first. The water is at a lower temperature. You see, this is what's going to happen. Even though it is 1,000 degrees Fahrenheit on the outside, which makes it sound like it should burn the paper, remember, the paper conducts. Now, not very well, I admit it. That's why what I did was take one of these little kids' cups that has the bottom that's really, really thin. And so even though the paper doesn't conduct that quickly, it's thin. That's why I also wrapped a piece of paper around that wood and the aluminum. Again, paper doesn't conduct that quickly, but it's thin. And so what will end up happening is it will take the energy and transfer it through the paper in the bottom of the cup and begin to warm the water